Okay, so welcome back to the next lecture in this week, and this week I plan to talk about information theory and entropy, which is a notion that kind of explains what happens in this when we talk about like uncertainty of the random walk, or like for example this idea of like when we shuffle cards and we try to like find the optimal way to shuffle and to get into a way that we don't really know what the state of the deck, for example, is. And for this purpose, like information theories are something which allows you to kind of formalize this notion of uncertainty. And for this purpose, like we can define the notion information formally. So information is a quantity that actually it's just defined to be the following function. So let mu be a probability distribution in ZP, and we define the information of mu at t in ZP as this function I mu at t to be just equal to the minus of the logarithm of mu t. So here this logarithm is with any base you want to choose, but usually fix it to be some base. It's usually like it depends on the kind of the model or the statistics you consider, or if it's like for example, in computer science, typically it's a base 2 logarithm if you're studying like binary sequences and they're compressing their information. But in here, I'm just going to use the natural logarithm. So this is the natural logarithm. And this will be in the whole course. We'll just use the natural logarithm. And what this quantity kind of gives you is that it kind of gives you like the amount of uncertainty you have with giving a choice. So given like a random choice, and what we want to like always study is kind of like an expected value of this. That what is the kind of expected uncertainty you expect to make a random choice. So that's why you define this notion of entropy. Let's go with the entropy. As the follows, that the entropy of a probability distribution mu is just this quantity gets called h mu, which is the expected information. So we could use this kind of notion to use this expectation of mu of this information function mu. If you remember the definition of expectation, this is the same as if you integrate this was the notation we used earlier also, or you can also like just formally define it. We use this notation as well, mu I mu, and if you want kind of what is, if you open this up it's just integral ZP mu t logarithm of mu t, which it comes out. So that's the notion of entropy if you look into this definition. So what it does is that because the information, it kind of tells you like when you make a random choice with and choose a random point with respect to mu, it tells you how much information or uncertainty this random choice has. So the reason for this is that this entropy, or the information here, that if this is very large, like in the sense of like it's close to like a large value at most points t, then there is like a lot of uncertainty in the choice. And at the same time, if this information function is very close to like, let's say being close to being 0, then you don't have much like information. So one thing that maybe to take into account when you compute the information, so there's a convention here that makes like everything like work in a way that otherwise you would have an issue, is that 0 times log of 0 is you just define this to be 0. And it's because of like there will be some measures or probability distributions where there's no mass at some points t, so that's why you need to define this convention that 0 times log 0 is 0. Which comes from basically this idea that somehow the polynomial, it's a linear function x is growing, is going to 0 like faster than maybe the log 0 or log x, but you like basically think that the limit of this x log x converges to 0 anyway as x goes to 0. So what we then can do is that we can study all the possible values. So this is examples. We have that in ZP, if you take the uniform distribution, lambda t is 1 over p in ZP, then we obtain that the entropy of this lambda, if you just start computing it, this becomes 1 over t in ZP, 1 over p log 1 over p, that's by the definition, and that's just the log p if you open this up, because this is basically the minus cancels out the minus 1 and there's an average over this, so you get the same value log p. And then we also get that if we fix some t0 in ZP and consider this Dirac mass at t0, t, which is again 1 and 0, t is equal to t0, t not equal to t0, then the entropy of this Dirac mass at t0, when you do the computation, you actually just see that in the summation everything is basically 0 except one position, so which is 1 times log of the log of 1 at the point t0, so you just get basically what is log of 1, that's equal to you get basically 0 at this stage. So what you have obtained, that you have basically seen that the in the uniform case where all the mass is kind of spread around the group, you have like maximal possible entropy, whereas if you have concentration around one point, you have very minimal entropy. So what you basically have here is this kind of idea that this is actually maybe you could think about this as a lemma, that this entropy for any mu probability distribution we have that the entropy is always between these two values. So this like maximal entropy, which is the log p, which is the entropy of the uniform distribution. This was the entropy of like any fully concentrated Dirac distribution. So you can check this lemma, you can prove this by yourself if you want. It's basically an application of, you can do this like using concavity properties, for example, if you want, like of the logarithm function, if you want. Like basically if you see what this is asking you to do is that if you have like general weights, then you're like trying to maximize some kind of a concave function, or in this case if you put the minus like a convex function, and then you can see the maximum comes in that one point. And this can be done, for example, in many ways. You can use Lagrange multipliers. You can use other like various like methods to check this. This is a standard kind of inequality for logarithm. Something called Jensen's inequality. If someone has heard about that, you can prove this. But we don't need to do this in this course. We just like want to mention that this is like basically shows the minimal and maximal entropies, and then. What we can do with this is this is kind of like an interesting theorem, that it actually does connect to the total variation distance. So there is this theorem which is called the Pinskers Inequality. I will not prove this in the lecture, but it's written. The proof is written in the notes, so you can have a look at that proof. And it's basically just saying that you can connect this in the case of, so in ZP we have the following, that the total variation distance between mu and the uniform distribution, so remember this is kind of like what we would like to measure sometimes that how uncertain something is, then you can actually measure it by basically the I think there's a constant. I think this should be fine with this constant h lambda, and then here you some constant. I think this 2 might be. You could maybe it's 4, but at least yeah, there's some constant that you get, and then I think this is 1 over 2 h lambda plus 1, and then h mu minus h lambda. I remember that this here and that here is log p. Log p. So here this one is where is log p. So what to take from this Pinskers inequality is just that you can basically bound the total variation distance from above and below by the distance to the maximal entropy. So this kind of shows that there is like a way of like if you're able to bound how well your measure is close to the uniform distribution in terms of entropy, you can immediately bound it by the total variation distance. And the proof of this is you just using like this. It's basically you could something called Cauchy-Schwarz inequality and other things. But you can look at the proof in the notes that you can see that there's a way to bound these expressions. And so that's kind of the main thing. So we will not, you don't need to use this in the exam. So this is only for the like, just for, yeah, that you know this exists, this kind of notion of Pinskers inequality, what we have. But the proof idea is interesting. So you can see how this kind of like, how do you connect this kind of L1 identity type of a notion into the entropy, which is an interesting to see. And a final thing I wanted to mention before the end of this this lecture is basically this formula, another type of a connection of total variation. So we had this like a variational principle, which is something that is very briefly mentioned in the notes. I will mention this basically here. It's also called variational formula. And I wanted to mention this just at the end now, because this kind of explains to you what is the reason why we call this a total variation distance. And it's not related to information and entropy anymore, but it has some connection to it, like deeply, if you we will later on see. So the theorem basically, in the notes this is theorem 2.29, and it says the following, that the total variation distance between two probability distributions is a half of the maximum of mu f minus nu f, where we take here the L infinity norm of the function being at most 1 for any f from ZB to R. So what here is the L infinity norm? So we haven't defined yet the L infinity norm, so we defined the L1 norm, but this is just the maximum of the absolute values of Ft and T in ZB. So, and this, remember that this was the integral, so this is just basically the, if we define this whole thing, then this whole thing over here is just equal to, we get the summation of f in ZB, and then we get Ft and mu T minus nu T as the whole expression that you have here. So that was the definition of the integral. And the reason for this is why this is called a variational formula, is because you're basically maximizing some type of like all the possible functions. So you may not like get the maximum, like we already see that like this kind of an expression that we consider here when we have the L1 identity, it had something similar going on with it. So it had like this half of the summation of the things, and we take the indicator function of the function b that maximized that kind of like situation. So this is in general that you have this kind of like is kind of almost like a functional analytic formula, where you're taking all the possible functions and then maximizing the kind of variations, that in a sense, that what's the maximal possible variations these functions have with respect to these two measures. And then you have this kind of like a notion of maximal number. So this also is something which is not proved in the notes, but this has been done in the exercises. So you can like try to see this exercise, and also in previous year exams, this has been an exam question of proving this formula. The proof of this is very similar to the L1 identity in many ways, that you just need to choose the right function f that maximizes this thing, and you get using you could use the L1 identity, for example, of proving that, and then this kind of like similar kind of like a going through the kind of arguments of L1 identity, and you can get the proof of this. So just to keep you in mind that this kind of formulas as well exist for the entropy, the total variation distance. Okay, I think this is all I wanted to say in this lecture. So as I mentioned, so we gave you an idea of what is an information, we gave you something about the notion of entropy, and then the variational principle. And all of these are like basically ways to maybe have a different formula or different expressions for the total variation distance, all kind of like a distance to a uniform distribution. And in the next week, we will start to go more into this notion of random walks and convolutions and other things, which then we can connect to this machinery of all these like total variation distance and other notions we've talked about so far.